Hello, I'm Renzo from NIH, and this is work by Marco Barilari, who cannot make it in person. And the title of this talk is The layer-fMRI-toolbox helps to automatize high-resolution whole-brain layer segmentation in volume space with minimum manual editing. And I have no financial interest to declare with respect to this presentation. The layer-fMRI-toolbox is trying to serve the emerging field of human layer-dependent fMRI, and this field is relatively old, however it has really caught on in the last 10 years with many human application studies, and is also being transformed just in the last 5 years since COVID. So ever since, studies are being done differently. For example, the sample size of participants per study is really going up, requiring more streamlined analyses, not allowing the operators anymore to do a lot of manual interventions. The fractions of studies that make their data publicly available for further analysis has doubled, and with the help of more standardized pipelines, we can take advantage of these additional free datasets that are now available to the field. The used software packages for layer segmentation also have shifted quite a bit, requiring a flexible combination of these tools that are out there. And last but not least, the used contrasts have moved away from only gradient and echo bold, with the majority of layer-fMRI studies now using a combination of more complex contrasts, for example, including Koiso. And all of these challenges need to be considered when doing layer-fMRI analyses. And the layer-fMRI toolbox that I want to present to you today is the first step towards a more standardized pipelines providing high-quality layer segmentation. Though, developing a standardized pipeline is hard, because layer-fMRI is versatile, and in the field of layer-fMRI, reproducibility should not be confused with homogeneity. So layer-fMRI is different than 3 Tesla processing. For conventional 3 Tesla fMRI processing, there exist standardized pipelines like fMRI prep. While for layer-fMRI, we need to combine many softwares, and very often looking at the research field of layer-dependent fMRI, there are as many pipelines as there are projects. To use the beer wine metaphor here, 3 Tesla processing is like producing beer. There are international standards and brands of beer corporations. No matter where you are in the world, it just works. Different for layer-dependent fMRI. It's more like wine producing. There are no international standards of wine production. Rather, you need to consider the local features of your specific study. You need more manual interventions and trainings. There are many software solutions out there already, and usually the number of software solutions that exist is directly inversely proportional to how well they work, because everybody tries it, it doesn't work, so they develop their own. And the top of the quality problem here is gray matter segmentation, where it takes up to 60 hours of manual labor per participant to get an excellent gray matter segmentation across the entire brain. For segmentation, there are 2 common approaches out there. One is manual segmentation of gray matter, and then using Laney to estimate the layers based on that, which is incredibly time consuming, specifically if you have large RIs. Secondly, a popular approach is to use free surfer gray matter segmentation from high resolution structural images, for example MP2 range, and then pumping a spatially upsampled version of this through Laney, which is not great either. Specifically, often we have segmentation inaccuracies, for example, things like the kissing gyri problems, where touching gyri are coming too close to each other, so we are missing the superficial layers. And here you can see people struggling with this all across the literature, with these kissing gyri not being segmented on their own, and then having kind of these missing superficial layers, including in some of the studies of our own. So the layer-fMRI toolbox wants to make the step easier. It uses a free-surfer-Laney combination as commonly used, but it improves it by adding data preparation, corrections, and piping it through a bunch of available packages out there, which are all designed to maintain the topology and translating between the data types of vertices and voxels back and forth. And you can appreciate the difference in performance here. And you can see how the kissing gyri are well preserved and resolved now, while also having explicit breakpoints in the pipeline for manual corrections of gray matter segmentations directly in voxel space where the layers will live at the end. Well, and that's it. You can grab the pipeline from GitHub up here and use it now. The layer-fMRI toolbox is a bit demanding with respect to computational resources. However, it is suitable for modern laptops as well as for server clusters, of course. It has been applied in a number of ongoing projects already, suggesting its scalability and generalizability, which I would like to show you a few examples from now. For example, In this project here, we are using an inversion recovery EPI sequence to capture functional changes of brain structure. So simultaneously, we are scanning whole brain bold, as well as MP2 range-like uni images with volume TRs of 20 seconds because it's EPI, and we do so during a visual block design. Now the layer-fMRI toolbox then really helps to segment hundreds of time points of this whole brain structural time series, revealing how cortical thickness changes as a function of activation. With the interesting result here that gray matter seems to dilate during functional activation. Specifically, it dilates into white matter, which is specific to the visual activated areas, and we don't see these dilations in control areas, for example, in the frontal cortex. Another application study of the layer-fMRI toolbox tries to investigate the perception of motion in congenitally blind people as well as in normally sighted controls, using vision motor tasks in the sighted and then also auditory motion tasks in both the sighted and the blind people. And the interesting finding here is that for blind people, they seem to use their visual motion perception area V5 as an area of auditory motion perception via feed-forward input pathways dominated from the middle feed-forward input layers, which is not the case for auditory motion perception in this area of sighted people, that rather seems to be dominated from feedback negative input in V5, suggesting that for blind people the hierarchical neural processing is rewired. And all of this is only visible as clearly across so many people in so many ROIs because of the smooth processing in the layer-fMRI toolbox. And last but not least, the layer-fMRI toolbox is also successfully applied in a connected study aiming at structural layer-MRI estimates of myelin content. So here the study is interested in the layer-MRI profiles of 8 ROIs in 24 participants. And in this project, it was particularly helpful to perform manual editing after the topology correction would undo it again, isolated to these few areas over here across so many participants. In conclusion, the layer-fMRI toolbox provides high-quality layers and a solution to the kissing gyres problem. It reduces manual labor, and we do think that it helps the field to get a step closer to a standardization in layer-fMRI processing where possible. Check it out on GitHub. We are happy for any contributions, and with this, I thank you for your attention.